Imagine this. You're in a bustling city at night, lights twinkling like stars, and suddenly, all the buildings, cars, and people start moving in unison, as if guided by an invisible hand. That's the cosmic dance happening right now in our universe. And the invisible hand? That's dark matter. It's the unseen architect, the cosmic glue holding galaxies together. Without it, everything would fly apart, and our universe would look like a bad traffic jam. So, buckle up as we dive into the mysterious world of dark matter, the invisible force that's been pulling the strings of our universe since the beginning of time. The cosmic enigma. In the vast expanse of the cosmos, galaxies spin and dance in a ballet of celestial mechanics. Yet, something unseen is pulling the strings, an invisible force that holds these galaxies together. This enigmatic force is dark matter, a cosmic conundrum that has baffled astronomers for decades. It doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is betrayed by the gravitational effects it exerts on visible matter. Think of it as an invisible puppeteer, guiding the visible stars and galaxies with unseen strings. The evidence for dark matter is compelling. Galaxies rotate much faster than they should, given the visible matter they contain. This is akin to a car rounding a sharp curve at high speed without the benefit of friction to keep it on the road. The only explanation is an unseen mass providing the necessary gravitational pull. Similarly, the bending of light around massive cosmic structures, a phenomenon known as gravitational lensing, often reveals more mass than we can account for with visible matter alone. It's as if we're seeing a mirage, a distorted view of reality that hints at something more substantial lurking in the shadows. Clues about dark matter's nature come from its interactions, or lack thereof, with ordinary matter. Unlike dark energy, which is thought to be responsible for the accelerating expansion of the universe, dark matter seems to interact only through gravity. It doesn't participate in the other fundamental forces, making it a ghostly presence in the cosmos. Scientists have proposed various candidates for dark matter, including WIMPs, weakly interacting massive particles, and axions, but none have been definitively detected. The search continues, a cosmic detective story that has captivated the minds of physicists and astronomers alike. The quest to understand dark matter is not just an academic pursuit. It's a journey to unravel the very fabric of the universe. Without dark matter, galaxies as we know them wouldn't exist. The cosmos would be a vastly different place, a tapestry of scattered stars and gas clouds, devoid of the grand structures we observe today. Dark matter is the invisible scaffolding upon which the visible universe is built. And until we solve this cosmic enigma, our understanding of the universe will remain incomplete, a puzzle with missing pieces. A universe veiled in darkness. In the vast expanse of the cosmos, a silent, invisible force weaves through the fabric of the universe, binding galaxies together like an unseen cosmic glue. This enigmatic entity, known as dark matter, constitutes approximately 27% of the universe's total mass and energy content. Yet, it remains elusive, detectable only through its gravitational effects on visible matter. It's as if the universe is a grand stage, and dark matter is the unseen puppeteer, pulling the strings that govern the motion of galaxies. Picture a spinning carousel, its horses and chariots whirling in a dazzling display. Now, imagine that the carousel is spinning so fast that the horses threaten to fly off into the night. Yet, they remain in place, held by an unseen force. This is akin to the role dark matter plays in galaxies. Stars and gas clouds at the edges of galaxies are moving so fast that they should escape the gravitational pull of the visible matter present. However, they don't. Something else, something invisible, is exerting a gravitational force, keeping them in check. This something is dark matter. The nature of dark matter is one of the most profound mysteries in modern astrophysics. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred through its gravitational influence on visible matter, such as stars and galaxies. For instance, the rotation curves of spiral galaxies, graphs that plot the orbital velocities of visible objects as a function of their distance from the galaxy's center, reveal a puzzling pattern. Instead of decreasing with distance, As expected from the distribution of visible matter, the curves remain flat. This anomaly suggests the presence of a massive, invisible halo of dark matter surrounding the galaxy. The quest to understand dark matter is akin to solving a cosmic whodunit. Scientists have proposed various candidates for dark matter, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. Each candidate has its own set of theoretical predictions and experimental signatures. Yet, despite decades of research, dark matter remains undetected in laboratory experiments. The mystery deepens, and the universe continues to veil its secrets in darkness. The search for dark matter is not just a scientific endeavor. It's a journey into the heart of the unknown, a quest to unravel the fabric of the cosmos itself. The visible and the invisible. In the vast cosmic ballet of galaxies, stars, and planets, there's an unseen choreographer pulling the strings. This mysterious force is dark matter, an invisible entity that makes up approximately 27% of the universe's total mass and energy content. It's a cosmic glue that holds galaxies together, preventing them from tearing apart due to their own spin. Yet, it doesn't emit, absorb, or reflect any electromagnetic radiation, making it invisible to our telescopes. It's like a ghostly puppeteer, its presence inferred only through the gravitational effects it has on visible matter. Picture a spinning merry-go-round. If you could somehow see only the horses and not the central pole, you'd wonder what's keeping them in their circular paths. That's similar to our view of galaxies. We see the stars, the glowing nebulae, and the swirling dust, but we can't see the dark matter that's keeping them in their cosmic dance. Its presence is betrayed by the gravitational pull it exerts, a silent whisper in the dark that scientists have been trying to decipher for decades. Dark matter's invisibility isn't just a matter of it being too faint to see. It's fundamentally different from the ordinary matter we're familiar with. Ordinary matter, or baryonic matter, interacts with light and other electromagnetic radiation, which is why we can see it. Dark matter, on the other hand, doesn't interact with light at all. It's like trying to spot a completely black cat in a coal cellar. You might know it's there because you can feel its fur or hear it purr, but you can't see it. This is why scientists rely on indirect methods to study dark matter, like observing its gravitational effects on visible matter or analyzing the cosmic microwave background radiation, the afterglow of the Big Bang. The visible universe, the one we can see and interact with, is like the tip of a cosmic iceberg. The vast majority of the universe's mass is hidden beneath the surface, invisible to our current instruments. This invisible component, dark matter, shapes the structure and evolution of the universe. It's the unseen architect of the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. Without dark matter, galaxies wouldn't have formed, stars wouldn't have ignited, and life as we know it wouldn't exist. It's a humbling thought, realizing that we owe our existence to an invisible force we're still struggling to understand. Galaxies, islands of mystery. Billions of stars, gas, dust, and dark matter coalesce into vast, spinning cities of the cosmos. Galaxies, these islands of mystery, are the fundamental building blocks of the universe's large-scale structure. They come in various shapes and sizes, from majestic spirals with sweeping arms to elliptical giants and irregular blobs. Our own Milky Way, a barred spiral galaxy, is a sprawling metropolis of stars, with a supermassive black hole at its heart, around which everything orbits in a cosmic dance. Picture a galaxy as a vast, dark ocean, with stars as tiny, flickering lanterns bobbing on the surface. The visible matter, stars, planets, gas, and dust, accounts for only a fraction of a galaxy's mass. The rest is an invisible force, a mysterious substance we call dark matter. It doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is betrayed by its gravitational pull, shaping the very structure of galaxies and holding them together. Without dark matter, galaxies would tear themselves apart, their stars flinging off into the intergalactic void. The nature of dark matter is one of the most profound mysteries in astrophysics. It's not made of the same stuff as stars and planets. Instead, it's a different kind of matter, a cosmic phantom that interacts with the visible universe only through gravity. Scientists have proposed various candidates for dark matter, from weakly interacting massive particles, WIMPs, to hypothetical particles like axions. Yet, despite decades of searching, its true nature remains elusive. It's as if we're trying to understand the ocean by studying only the surface waves, knowing full well that vast, unseen depths lie beneath. Galaxies are not static islands. They evolve, interact, and sometimes collide in spectacular cosmic dances. When two galaxies meet, their dark matter halos can merge, creating a complex web of invisible matter that shapes the new galaxy structure. These interactions can trigger bursts of star formation, as gas and dust are compressed and ignited into new stellar life. Yet, even in these dramatic events, dark matter remains unseen, its presence inferred only through its gravitational effects. It's the silent architect of the cosmos, the invisible force that binds galaxies together and shapes their destiny. The puzzle of galactic rotation. In the vast cosmic ballet of galaxies, stars pirouette around their centers in a mesmerizing display of celestial mechanics. Yet, this dance holds a profound mystery. Observations reveal that stars far from the galactic center orbit at speeds comparable to those closer in, defying the gravitational pull predicted by visible matter alone. This incongruity suggests an unseen force at play, a cosmic puppeteer pulling strings we cannot see. The puzzle of galactic rotation has led astronomers to a tantalizing conclusion. Dark matter, an invisible substance, permeates galaxies, exerting gravitational influence without emitting light. Picture a whirlpool, its outer edges spinning as swiftly as its core. This is the scenario in galaxies, where the outer stars should, by rights, move slower than their inner counterparts, much like the outer edges of a spinning disk. But they don't. This discrepancy is the galactic rotation problem, a cosmic conundrum that has perplexed astronomers for decades. The only explanation that fits is the presence of dark matter, a mysterious substance that doesn't interact with light but exerts a gravitational pull. It's like an invisible hand, shaping the dance of stars without ever stepping into the spotlight. To understand the scale of this puzzle, consider the Milky Way. Stars at its outer edges rotate at about 220 kilometers per second, just like stars near the center. This uniformity suggests that the mass of the galaxy isn't concentrated at the center, but is instead spread out in a vast, invisible halo. This halo, composed of dark matter, extends far beyond the visible boundaries of the galaxy. It's a cosmic enigma, a force we can't see but can infer through its gravitational effects, much like deducing the presence of an unseen iceberg from the disturbance it causes in the water. The evidence for dark matter isn't just theoretical. It's observed in the behavior of galaxies, the bending of light around massive objects, and the cosmic microwave background radiation. Yet, despite its pervasive influence, dark matter remains elusive. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred solely through its gravitational effects, a cosmic whisper in the dark. This invisible force, holding galaxies together, remains one of the most profound mysteries in astrophysics, a puzzle that continues to challenge our understanding of the universe. The missing mass problem. In the vast cosmic ballet of galaxies, stars pirouette around their centers with a grace that seems almost effortless. Yet, this celestial dance hides a profound mystery. When astronomers began to calculate the mass of galaxies based on the visible matter, stars, gas, and dust, they encountered a perplexing discrepancy. The calculated mass was insufficient to account for the gravitational forces holding these galaxies together. This conundrum is known as the missing mass problem. It's as if you were watching a tightrope walker perform an intricate routine, only to realize that the rope they're balancing on is far thinner than it should be to support their weight. Something invisible must be providing the necessary support. To understand the missing mass problem, consider the spiral galaxy, a common sight in the night sky. The outer regions of these galaxies rotate at speeds that defy the gravitational pull exerted by the visible matter. According to the laws of physics, the outer stars should be moving slower than those closer to the center. However, observations show that stars in the outer regions move at nearly the same speed as those near the center. This can only be explained if there is an unseen mass exerting a gravitational influence. This invisible mass is what scientists refer to as dark matter. It's like having a party where the music is loud and the lights are dim, but you can't see anyone dancing. You know they're there because you feel the vibrations, but you can't pinpoint their exact locations. The missing mass problem isn't just a theoretical curiosity. It has practical implications for our understanding of the universe. Dark matter is thought to make up about 27% of the total mass energy content of the universe, far outweighing the visible matter that makes up only about 5%. This invisible scaffolding shapes the large-scale structure of the cosmos, influencing the formation and evolution of galaxies. Without dark matter, the galaxies we see today might not exist. It's akin to the unseen framework of a building, providing the necessary support and structure that allows the visible parts to stand tall and proud. Yet, despite its crucial role, dark matter remains elusive, detectable only through its gravitational effects. Efforts to detect dark matter directly have so far been unsuccessful. Scientists have proposed various candidates for dark matter, including weakly interacting massive particles, WIMPs, and axions, but none have been conclusively identified. The search for dark matter is ongoing, with experiments like the Large Hadron Collider and the Dark Energy Survey aiming to shed light on this cosmic enigma. Until then, the missing mass problem remains one of the most intriguing puzzles in modern astrophysics, a testament to the universe's ability to keep us guessing. It's a reminder that there's still so much we don't understand, and that the cosmos is full of mysteries waiting to be unraveled. Zwicky's dark matter hypothesis. In the vast, star-studded canvas of the cosmos, galaxies pirouette in a mesmerizing dance, bound together by an unseen force. This force, dark matter, is a cosmic glue that defies detection, yet its presence is undeniable. The story of dark matter begins with Fritz Zwicky, a Swiss astronomer who, in the 1930s, turned his gaze towards the Coma Cluster, a dense congregation of galaxies. Zwicky was no ordinary stargazer. He was a pioneer, a maverick who challenged the scientific norms of his time. He noticed something peculiar. The galaxies in the Coma Cluster were moving at velocities that defied the gravitational pull of the visible matter. It was as if an invisible hand was holding them together, preventing them from flying apart. This observation led Zwicky to propose a radical idea. There must be a substantial amount of unseen matter, which he dubbed dark matter, exerting a gravitational influence on the visible galaxies. Zwicky's hypothesis was met with skepticism. After all, how could one prove the existence of something that was, by definition, invisible? Yet, Zwicky was undeterred. He calculated that the total mass of the Coma Cluster, based on the velocities of its galaxies, was at least 400 times greater than the mass of the visible matter. This staggering discrepancy hinted at the presence of a vast amount of dark matter. It was like trying to weigh a ghost. You couldn't see it, but you could feel its presence through its gravitational tug. Zwicky's work laid the foundation for future explorations into the nature of dark matter, even if his contemporaries were slow to accept his ideas. The concept of dark matter gained traction decades later when Vera Rubin and Kent Ford studied the rotation of galaxies. They found that the outer regions of galaxies rotated at the same speed as the inner regions, a phenomenon that could not be explained by the visible matter alone. This was another piece of the puzzle, another clue pointing towards the existence of dark matter. Zwicky's initial hypothesis, once dismissed, was now gaining credibility. The invisible force he had postulated was essential for explaining the dynamics of galaxies and galaxy clusters. It was the cosmic glue that held the universe together, even if it remained elusive to direct detection. The search for dark matter continues to this day, with scientists employing a variety of methods to uncover its nature. From particle physics experiments to astronomical observations, the quest to understand dark matter is a testament to human curiosity and ingenuity. Zwicky's dark matter hypothesis, once a radical idea, is now a cornerstone of modern astrophysics. It reminds us that the universe is full of mysteries, waiting to be unraveled. And in the grand tapestry of the cosmos, dark matter is a thread that weaves through it all, binding galaxies together in a dance that has been going on for billions of years. The verification of dark matter. In the vast, star-studded canvas of the cosmos, Galaxies are like cosmic cities, bustling with activity and held together by an unseen force. This force, dark matter, is as elusive as it is essential. It doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is betrayed by the gravitational effects it exerts on visible matter. The verification of dark matter is a thrilling detective story, a cosmic whodunit that has kept astronomers on the edge of their seats. Picture a spinning merry-go-round. If you were to place a heavy weight on one side, the merry-go-round would spin faster, right? Now, consider galaxies as cosmic merry-go-rounds. Stars are like the lightweights on them. When astronomers observe galaxies, they notice something peculiar. The stars at the edges were moving as fast as those near the center. This was unexpected. It was as if an invisible weight was tugging at the edges, making the galactic merry-go-round spin faster than it should. This was one of the first clues pointing towards dark matter. But how do you verify something you can't see? Astronomers turn to a phenomenon called gravitational lensing. Imagine looking at a distant light through a wine glass. The glass bends the light, creating a distorted image. Similarly, massive objects in space, like galaxies, bend the light from objects behind them. By studying these distortions, astronomers can map the gravitational field of the galaxy. The results were astonishing. The gravitational fields were too strong to be explained by visible matter alone. Something invisible was adding to the gravitational pull. This was strong evidence for dark matter. Yet, the story doesn't end here. Another piece of the puzzle came from the cosmic microwave background, CMB, the afterglow of the Big Bang. Tiny fluctuations in the CMB provided a snapshot of the early universe. These fluctuations revealed that only about 5% of the universe's matter is visible. The rest is dark matter. This cosmic fingerprint confirmed what astronomers had suspected all along. Dark matter is the invisible force holding galaxies together, the unseen architect of the cosmos. The verification of dark matter is an ongoing journey, a testament to human curiosity and our quest to understand the universe. The nature of dark matter. In the vast cosmic ballet of galaxies, stars, and planets, there's an unseen dancer pulling the strings, an invisible force that holds everything together. This enigmatic entity is dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, making it invisible to our current telescopes. Yet, its presence is betrayed by its gravitational effects, much like a ghostly hand stirring a cup of tea, leaving ripples in its wake. Scientists estimate that dark matter makes up about 27% of the universe's total mass and energy content, far outweighing the ordinary matter that makes up stars, planets, and all visible structures. Picture a spinning galaxy, a pinwheel of stars and gas. According to the laws of physics, the outer stars should be flung out into the darkness, like water droplets from a wet dog's shake. But they're not. They orbit peacefully, bound by the gravitational pull of something unseen. This is the first hint of dark matter, a cosmic glue that holds galaxies together. It's not just galaxies, either. Entire clusters of galaxies are bound together by dark matter, like a giant, invisible net. Without it, the universe as we know it would fly apart, stars scattering like marbles on a floor. So what is this dark matter? That's the million-dollar question. We know it's not made of the same stuff as stars and planets. It doesn't interact with light, so it's not atoms or molecules. It's not dark clouds of gas or dust, either. These would absorb and emit light, and we'd see their silhouettes against the bright backdrop of the universe. Dark matter is something else entirely, a substance that's as elusive as it is essential. Scientists have proposed various candidates for dark matter, from weakly interacting massive particles, WIMPs, to hypothetical particles like axions. But so far, none have been definitively detected. It's a cosmic whodunit, with the universe holding the clues. WIMPs, weakly interacting massive particles. In the vast, dark expanse of the universe, galaxies spin and dance in a cosmic ballet. Yet, something invisible is pulling the strings, an unseen force that holds these celestial bodies together. This enigmatic force is dark matter, and one of the leading candidates to explain its nature is the weakly interacting massive particle, or WIMP. WIMPs are hypothetical particles that interact with normal matter through gravity and the weak nuclear force, but not the electromagnetic or strong nuclear forces. This makes them incredibly elusive, passing through ordinary matter like ghosts through walls. To understand WIMPs, think of them as cosmic ninjas. They don't emit, absorb, or reflect light, making them invisible to telescopes. They don't interact with the strong nuclear force, so they don't bind together to form atoms. They only interact through gravity and the weak nuclear force, which is why they're so hard to detect. Yet, their gravitational influence is undeniable. They act like invisible scaffolding, providing the extra mass needed to explain the observed gravitational effects in galaxies and galaxy clusters. The search for WIMPs is like looking for a needle in a cosmic haystack. Scientists use underground detectors, shielded from cosmic rays, to search for the tiny flashes of light or electrical signals that might occur when a WIMP bumps into an atomic nucleus. These detectors are often located deep underground, in mines or tunnels, to shield them from background radiation. The hope is that one day, these elusive particles will leave a telltale sign of their presence, confirming their existence and helping us unravel the mystery of dark matter. The stakes are high. Finding WIMPs could revolutionize our understanding of the universe. They could provide a missing piece in the puzzle of how galaxies form and evolve. They might even offer insights into the fundamental forces of nature. But the search is far from easy. WIMPs are, by their very nature, weak and elusive. Yet, the scientific community remains undeterred. The quest for these cosmic ninjas continues, driven by curiosity and the desire to understand the invisible force holding galaxies together. Axions, a theoretical particle. In the vast, dark expanse of the universe, galaxies spin and dance in a cosmic ballet, bound together by an invisible force. This force, dark matter, is a mysterious substance that doesn't emit, absorb, or reflect light, making it invisible to our current telescopes. Among the many theoretical particles proposed to explain dark matter, axions stand out as one of the most promising candidates. They are hypothetical particles that are incredibly light, possibly even ultralight, with masses ranging from a fraction of a microelectron volt to a few electron volts. To put that into perspective, that's a fraction of the mass of a single electron. Axions are also predicted to be extremely abundant, with potentially billions of them passing through every cubic centimeter of space on Earth every second. The idea of axions was first proposed in the late 1970s to solve a different problem in particle physics, the strong CP problem. This problem arises from the fact that the laws of physics seem to be symmetric under the combined actions of charge conjugation, C, and parity, P, transformations, yet there's no fundamental reason why this should be the case. Axions were introduced to restore this symmetry. Interestingly, the same properties that make axions a solution to the strong CP problem also make them an excellent candidate for dark matter. They are stable, weakly interacting, and light, all properties that are desirable in a dark matter particle. Axions are also unique because they are predicted to interact with each other and with ordinary matter in a way that could potentially be detected. One of the most promising ways to detect axions is through their interaction with electromagnetic fields. In the presence of a strong magnetic field, axions can convert into photons, a process that can be detected with sensitive equipment. Several experiments are currently underway to detect these photons, including the Axion Dark Matter Experiment, ADMX, and the Cosmic Axion Spin Precession Experiment, CASPER. If axions are indeed the dark matter, these experiments could provide the first direct evidence of their existence. The search for axions is not just a hunt for a single particle, but a quest to understand some of the most fundamental aspects of our universe. If axions are confirmed to exist, they could provide insights into the nature of dark matter, the early universe, and even the fundamental laws of physics. They could also help us understand the strong CP problem, shedding light on why the laws of physics seem to be symmetric under the combined actions of charge conjugation and parity transformations. The search for axions is a testament to the power of theoretical physics, where abstract ideas can lead to profound insights into the nature of reality. MACHOs, massive compact halo objects. In the vast, dark expanse of the universe, galaxies spin and dance in a cosmic ballet, bound together by an invisible force. This force, known as dark matter, is a mysterious substance that doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is undeniable, its gravitational pull holding galaxies together, preventing them from tearing apart due to their own spin. One of the early candidates proposed to explain this phenomenon was MACHOs, or massive compact halo objects. These are objects that are massive, compact, and reside in the halo of our galaxy, the Milky Way. They could be anything from rogue planets, black holes, to brown dwarfs, failed stars that never quite made it to the main sequence. Think of them as the cosmic nomads, drifting through the galaxy, their presence betrayed only by their gravitational influence. The idea behind MACHOs is that they could be scattered throughout the halo of our galaxy, contributing to its mass and thus, its gravitational pull. Like a cosmic game of hide and seek, these objects are elusive, their presence inferred rather than directly observed. Scientists search for them using a technique called microlensing. This is akin to using a magnifying glass to find a tiny object. The MACHO acts as the magnifying glass, bending and focusing the light from a background star, making it appear brighter for a short period. It's a fleeting glimpse, a brief moment of revelation in an otherwise invisible dance. However, the story of MACHOs is not as straightforward as it seems. While they do exist, they don't appear to be as abundant as once thought. Early estimates suggested that MACHOs could make up a significant portion of the dark matter in our galaxy. But subsequent studies, like the MACHO and EROS projects, found that they could only account for a small fraction of the dark matter. It's like searching for a needle in a haystack, only to find a few needles, but not nearly enough to fill the haystack. This has led scientists to look for other candidates, like WIMPs, weakly interacting massive particles, to explain the missing mass in galaxies. The search for dark matter is ongoing, a testament to the enduring mystery of the universe. MACHOs, once a promising candidate, have been largely ruled out as the primary component of dark matter. Yet, their study has not been in vain. The techniques developed to search for them, like microlensing, have proven invaluable in other areas of astronomy. Moreover, the search for MACHOs has deepened our understanding of the universe, reminding us that the cosmos is full of surprises and that the journey of discovery is often as important as the destination. The dance of galaxies continues, bound together by an invisible force, a cosmic ballet that we are only beginning to understand. The search for dark matter. In the vast, dark expanse of the universe, galaxies spin and dance in a cosmic ballet. Yet, something unseen tugs at their edges, keeping them from flying apart. This mysterious force is dark matter, an invisible scaffold that holds galaxies together. Scientists have been on a relentless quest to uncover its secrets, much like detectives piecing together a complex puzzle. The search for dark matter is a tale of ingenuity, perseverance, and the unyielding human desire to understand the unknown. Picture a whodunit where the culprit leaves no fingerprints, no witnesses, and no direct evidence. That's the challenge scientists face. Dark matter doesn't emit, absorb, or reflect light, making it invisible to telescopes. Yet, its presence is betrayed by its gravitational effects, much like a ghostly hand stirring a cup of tea. To detect it, scientists have devised an array of clever experiments. Some look for the rare collisions between dark matter particles, others search for the faint glow of annihilation, and some even use the universe itself as a giant detector, studying the bending of light and the motion of stars. One of the most promising avenues is the search for weakly interacting massive particles, or WIMPs. These hypothetical particles are thought to interact with normal matter only through gravity and the weak nuclear force, making them exceedingly difficult to detect. Yet, deep underground, shielded from cosmic rays and other interference, detectors like the Large Underground Xenon Experiment, LUX, and the Xenon 1T experiment are on the lookout for the tiny flashes of light or the faint electrical signals that might betray a WIMP's presence. It's like searching for a needle in a cosmic haystack, but the stakes are high. Finding WIMPs could revolutionize our understanding of the universe. Another approach is to look for the signs of dark matter annihilation or decay. When dark matter particles collide, they might annihilate each other, releasing a burst of energy in the form of gamma rays, the highest energy form of light. Telescopes like the Fermi Gamma Ray Space Telescope scan the sky for these telltale signs, focusing on regions where dark matter is thought to be dense, like the centers of galaxies. Meanwhile, experiments like the Alpha Magnetic Spectrometer, AMS, on the International Space Station search for the positrons and antiprotons that might be produced in these annihilations. It's a high-stakes game of cosmic detective work, with scientists piecing together clues from across the universe. Dark matter detection techniques. In the vast, dark expanse of the universe, galaxies spin and dance in a cosmic ballet, bound together by an invisible force. This force, dark matter, is a mysterious and elusive entity that doesn't emit, absorb, or reflect light, making it invisible to our current telescopes. Yet, its presence is undeniable, its gravitational pull holding galaxies together, preventing them from tearing apart due to their own spin. Detecting this invisible force is one of the most significant challenges in modern astrophysics, a quest that has led to the development of ingenious techniques, each with its own strengths and limitations. One of the primary methods used to detect dark matter is through its gravitational effects. Think of it like trying to detect a black cat in a coal cellar. You can't see it, but you can infer its presence by its effects on the environment. Similarly, astronomers observe the gravitational influence of dark matter on visible matter, such as stars and gas clouds. For instance, the rotation curves of galaxies, which plot the orbital velocities of visible objects as a function of their distance from the galaxy's center, often reveal unexpected patterns that can be explained by the presence of dark matter. This technique is akin to observing the ripples on a pond's surface to infer the presence of a stone that you can't see. Another promising approach is the search for indirect evidence of dark matter particles annihilating or decaying into detectable particles. This is like trying to detect a silent, invisible intruder by the faint traces they leave behind. Dark matter particles, if they exist, could potentially annihilate each other, releasing a burst of energy in the form of gamma rays, the most energetic form of light. Satellites like NASA's Fermi Gamma Ray Space Telescope have been scanning the skies for these telltale gamma ray signals. Additionally, experiments on Earth, such as the Alpha Magnetic Spectrometer, AMS, aboard the International Space Station, are searching for an excess of positrons, the antimatter counterparts of electrons, which could also result from dark matter annihilation. Direct detection experiments, on the other hand, aim to observe the rare interactions between dark matter particles and ordinary matter. These experiments, conducted deep underground to shield them from cosmic rays and other background noise, use highly sensitive detectors to search for the tiny recoil energy deposited when a dark matter particle collides with an atomic nucleus. Think of it like trying to hear a whisper in a noisy room. The detectors must be incredibly sensitive to pick up these faint signals. Examples include the Large Underground Xenon LUX experiment and the Xenon 1T experiment, both of which use liquid xenon as the target material. Despite their sensitivity, these experiments have yet to yield a definitive dark matter signal, highlighting the elusive nature of this invisible force. The search continues, driven by the tantalizing promise of unlocking one of the universe's most profound mysteries: the role of gravity. In the vast cosmic ballet of galaxies, stars, and planets, there's an unseen dancer pulling the strings, an invisible force that keeps everything from spinning off into the void. This force is gravity, and it's the glue that holds galaxies together. But here's the twist: the gravity we observe isn't enough to explain how galaxies rotate. There's something else at play, something we can't see, something called dark matter. To understand this, picture a merry-go-round. If you see it spinning too fast for the children on it to stay in place, you'd suspect there's something unseen keeping them from flying off. That's the cosmic merry-go-round we're dealing with, and dark matter is the unseen force keeping it all together. Gravity, as we know it, is the weakest of the four fundamental forces, yet it's the one that shapes the large-scale structure of the universe. It's what makes apples fall from trees and keeps us grounded. But when we look at galaxies, something doesn't add up. Stars at the edges of galaxies move as if they're under the influence of much more mass than we can observe. This discrepancy suggests that there's a hidden component, dark matter, contributing to the overall gravity. It's like trying to weigh a truck by looking at its wheels. If the wheels alone don't account for the weight, you'd know there's more to the truck than meets the eye. The role of gravity in this cosmic mystery is twofold. First, it's the force that we observe acting on visible matter, like stars and gas. Second, it's the force that's seemingly being influenced by something we can't see. This is where dark matter comes in. It doesn't emit, absorb, or reflect light, making it invisible to our current detection methods. Yet, its gravitational effects are undeniable. It's like trying to navigate a room in the dark. You can't see the furniture, but you know it's there because you bump into it. Similarly, we can't see dark matter, but we know it's there because of its gravitational pull. The interplay between gravity and dark matter is a cosmic dance that's been going on for billions of years. It's a dance that's kept galaxies from flying apart, that's shaped the large-scale structure of the universe. And it's a dance that scientists are still trying to understand. They're like detectives, gathering clues, trying to piece together the mystery of dark matter. They use tools like gravitational lensing, where the gravity of a massive object, like a galaxy or a cluster of galaxies, bends and distorts the light from objects behind it. This distortion can reveal the presence of dark matter, even if it's invisible. It's like using a magnifying glass to find hidden clues. But the mystery remains, and the dance continues. Dark matter halos. In the vast, dark expanse of the universe, galaxies are not the isolated islands they might seem. They are enveloped in something far more mysterious and pervasive: dark matter halos. These halos are colossal, invisible structures that extend far beyond the visible boundaries of galaxies, exerting a gravitational influence that binds galaxies together. Think of them as the cosmic glue that holds the universe's structure intact. Without them, galaxies would fly apart, their stars scattering like marbles on a floor. Dark matter halos are not uniform. They have a complex structure, often described as lumpy or clumpy. This is because dark matter doesn't interact with itself or regular matter in the way we understand. It doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is betrayed by its gravitational effects. For instance, the way stars orbit within galaxies suggests the existence of a massive, invisible halo. It's like trying to understand the shape of an iceberg by observing the ripples it creates on the water's surface. The mass of these halos is staggering. They can be tens or even hundreds of times more massive than the visible matter in galaxies. This means that what we see, stars, gas, dust, is just the tip of the cosmic iceberg. The rest is dark matter, an unseen majority that shapes the universe's structure. Scientists study these halos using sophisticated computer simulations and observations of gravitational lensing, where the light from distant galaxies is bent by the gravitational pull of intervening dark matter. It's a bit like using a magnifying glass to see the invisible. Understanding dark matter halos is crucial for unraveling the mysteries of galaxy formation and evolution. They play a pivotal role in the cosmic web, the large-scale structure of the universe. Galaxies form at the nodes of this web, where dark matter is densest. The halos provide the gravitational scaffolding upon which galaxies are built. Without them, the universe as we know it wouldn't exist. It's a humbling thought, realizing that the vast majority of the universe's matter is invisible, yet it's the unseen force that holds everything together. Galactic formation and evolution. In the vast cosmic ballet, galaxies pirouette and twirl, their graceful movements a testament to the invisible hand of dark matter. This enigmatic force, making up approximately 27% of the universe's mass energy content, is the unseen architect of galactic formation and evolution. Without it, the universe as we know it would be a vastly different place, with galaxies struggling to form and evolve into the majestic structures we observe today. Picture a spinning ice skater pulling their arms in, speeding up their rotation. Similarly, dark matter's gravitational pull causes gas and dust to clump together, spinning faster and faster until a galaxy is born. This process, known as hierarchical clustering, begins with small, dense regions of dark matter that attract normal matter through gravity. Over time, these regions grow, merging and colliding to form the galaxies we see today. The Milky Way, for instance, is thought to have formed from the merger of smaller galaxies, a process that continues even now, with the Milky Way on a collision course with the Andromeda Galaxy in the distant future. Dark matter doesn't just help galaxies form, it also shapes their evolution. It's the cosmic glue that holds galaxies together, preventing them from tearing apart due to their own rotation. In spiral galaxies like our own, dark matter forms a vast, diffuse halo that extends far beyond the visible disk of stars. This halo's gravitational pull keeps the galaxy's stars and gas in check, allowing them to orbit the galactic center at high speeds without flying off into the intergalactic void. Without dark matter, the outer stars and spiral galaxies would be moving too fast to be bound by the gravity of the visible matter alone, a puzzle known as the galactic rotation problem. Moreover, dark matter influences the large-scale structure of the universe. It's the scaffolding on which galaxies and galaxy clusters form, their distribution tracing out the underlying dark matter structure. This cosmic web, as it's known, is a complex network of filaments and voids, with galaxies and galaxy clusters forming at the dense nodes and along the filaments. Dark matter's gravitational pull causes these structures to grow and evolve over time, shaping the universe on the largest scales. Yet, despite its profound influence, dark matter remains elusive, its nature and properties still shrouded in mystery. It's a cosmic enigma, the invisible force that holds galaxies together and shapes the universe as we know it. The cosmic web. In the vast expanse of the universe, galaxies are not scattered randomly like confetti. Instead, they are strung together in an intricate, web-like structure, a cosmic tapestry woven with invisible threads of dark matter. This is the cosmic web, a grand architecture that spans hundreds of millions of light years, with galaxies huddled together in dense clusters, connected by filaments of dark matter and surrounded by immense voids. It's as if the universe is a colossal sponge, with galaxies occupying the filaments and clusters, and the voids representing the empty spaces. The cosmic web is not just a static structure, it's a dynamic, evolving entity. Dark matter, which makes up about 27% of the universe's content, plays a pivotal role in this cosmic dance. It's the invisible force that binds galaxies together, acting as a gravitational glue. Without dark matter, galaxies would not have formed, and the cosmic web would not exist. Think of dark matter as the unseen scaffolding that holds the universe's structure in place. It's not just a passive participant, it actively shapes the distribution of visible matter, guiding the formation of galaxies and galaxy clusters. The filaments of the cosmic web are not uniform. They vary in density and thickness, creating a complex network that is both beautiful and functional. These filaments are not just highways for galaxies. They are also pathways for gas to flow, fueling star formation in galaxies. The densest regions of the cosmic web are where galaxy clusters form, while the filaments themselves are populated by groups of galaxies. The voids, on the other hand, are largely empty, containing very few galaxies. This distribution of matter is not random. It's a direct result of the gravitational influence of dark matter. Understanding the cosmic web is not just about mapping the universe. It's about understanding the very fabric of reality. The cosmic web is a testament to the power of gravity and the influence of dark matter. It's a reminder that the universe is not just a collection of isolated islands. It's a connected, interwoven whole. By studying the cosmic web, scientists hope to unravel the mysteries of dark matter and dark energy, the two most enigmatic components of our universe. It's a journey that takes us to the very edges of human knowledge, a journey that challenges our understanding of reality itself. Dark matter and dark energy. In the vast, star-studded canvas of the cosmos, there's an unseen puppeteer pulling the strings, making galaxies dance and spin. This elusive force is dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is betrayed by its gravitational pull, a cosmic fingerprint on the universe's fabric. Picture a bustling city at night, its streets alive with activity, yet shrouded in darkness. The city's layout, the flow of traffic, and the hum of life are all guided by unseen infrastructure, roads, traffic lights, and rules. Similarly, Dark matter is the unseen infrastructure of the universe, guiding the dance of galaxies and the flow of cosmic matter. Dark matter's existence was first hinted at in the 1930s when astronomers observed that galaxies were spinning too fast to be held together by the gravity of their visible matter alone. It's like watching a spinning plate on a stick. If it's spinning too fast, it should fly off, yet it doesn't. Something unseen must be providing extra gravity to hold it together. This unseen something is dark matter. It's estimated to make up about 27% of the universe's total mass and energy content, far outweighing the visible matter we can see and interact with. Now, if dark matter is the invisible glue holding galaxies together, dark energy is the enigmatic force causing the universe to expand at an accelerating rate. It's as if the universe is a balloon being inflated, not just by a steady breath, but by an ever-increasing gust of wind. Dark energy is thought to make up about 68% of the universe's total mass and energy content, making it the most prevalent component of the cosmos. Its discovery in the late 1990s was a monumental shock to the scientific community, as it defied our understanding of gravity and the universe's evolution. The interplay between dark matter and dark energy is a cosmic tug-of-war, shaping the universe's destiny. Dark matter pulls galaxies together, fostering the formation of stars and planets, while dark energy pushes them apart, driving the universe's expansion. This cosmic dance is a delicate balance, a symphony of forces that has led to the universe we see today. Yet, despite its profound influence, we know very little about dark energy. Its nature remains one of the most profound mysteries in modern physics, a tantalizing enigma that continues to challenge and inspire scientists worldwide. The interplay of light and darkness. In the vast cosmic ballet, galaxies pirouette in a mesmerizing dance, bound together by an unseen force. This force, dark matter, is as elusive as it is essential, weaving an intricate web that connects the luminous tapestry of stars and galaxies. It's a cosmic glue, invisible yet indomitable, shaping the universe in ways that light alone cannot. Picture a spider's web glistening with dew at dawn. The strands are the dark matter, invisible yet strong, holding the droplets of light, stars and galaxies, in place. Without this web, the universe would be a chaotic scattering of light, devoid of the structure and pattern we observe today. The interplay of light and darkness in the cosmos is a delicate balance, a cosmic seesaw. Light, in the form of stars and galaxies, is the visible manifestation of the universe. It's the glittering jewels that catch our eye and spark our imagination. Yet, for every gleaming star, there's an unseen counterpart, a shadowy entity that tugs and pulls, guiding the dance of the cosmos. Dark matter is estimated to make up about 27% of the universe's total mass and energy content, while the ordinary matter that makes up stars, planets, and everything we see accounts for only about 5%. This disparity highlights the crucial role dark matter plays in the cosmic ballet. The nature of dark matter remains one of the most profound mysteries in astrophysics. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. Yet, its presence is betrayed by its gravitational effects. For instance, the rotation of galaxies is too rapid for the visible matter alone to hold them together. There must be something else, something invisible, providing the extra gravitational glue. This is where dark matter steps in, its invisible hand guiding the dance of the stars. It's like a puppeteer in the shadows, pulling the strings that make the cosmic marionettes dance. The interplay of light and darkness is a cosmic symphony, with dark matter conducting the orchestra of stars and galaxies. The bullet cluster, a smoking gun. In the vast cosmic ballet of galaxies, there's an unseen dancer pulling the strings, an invisible force that holds these celestial bodies together. This enigmatic entity is dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is undeniable, its gravitational pull shaping the very fabric of the universe. One of the most compelling pieces of evidence for dark matter's existence is the bullet cluster, a spectacular collision of galaxy clusters that has been likened to a cosmic crime scene, with dark matter as the elusive perpetrator. Picture two massive galaxy clusters, each containing hundreds of galaxies, hot gas, and dark matter, hurtling towards each other at millions of miles per hour. In the bullet cluster, these two behemoths collided head-on, creating a spectacle of cosmic proportions. The hot gas in each cluster, which makes up the majority of the visible matter, slowed down and rammed into each other, like two high-speed trains coupling together. This impact sent shockwaves through the gas, heating it to tens of millions of degrees. Meanwhile, the galaxies themselves, like ghostly apparitions, passed through each other relatively unscathed, their immense distances ensuring they mostly avoided direct collisions. But the real drama unfolded in the invisible realm. Dark matter, which makes up about 85% of the matter in the universe, didn't behave like the visible gas or the galaxies. It didn't slow down or interact electromagnetically. Instead, it sailed right through the collision, its gravitational effects betraying its presence. This separation of dark matter from the visible gas was the smoking gun astronomers had been waiting for. It was the first direct evidence that dark matter exists and that it doesn't interact with ordinary matter in any way other than through gravity. This discovery was akin to finding a ghostly handprint at a crime scene, a tangible clue pointing to an invisible culprit. The bullet cluster story doesn't end there. By studying the gravitational lensing effects, where the gravity of the dark matter bends and distorts the light from background galaxies, astronomers were able to map out the distribution of dark matter in the cluster. This map revealed a dark matter core in each of the colliding clusters, with the cores passing through each other, untouched by the violent collision. This further cemented the idea that dark matter is not only invisible, but also doesn't interact with itself or ordinary matter in any way other than gravitationally. It's like having two invisible, intangible ghosts passing through each other, their presence only betrayed by the gravitational tug they exert on the visible world. The bullet cluster, with its dramatic separation of dark matter and visible gas, remains one of the most compelling pieces of evidence for the existence of dark matter, a silent, invisible force holding galaxies together in the grand cosmic dance. Alternative theories to dark matter. In the vast, star-studded canvas of the cosmos, dark matter is the unseen brushstroke that paints the structure of galaxies. It's the cosmic glue, the invisible hand that keeps galaxies from spinning apart, yet its nature remains elusive. But what if there's more to the story? What if dark matter isn't the sole architect of galactic structure? This is where alternative theories come into play, challenging our understanding of the universe and inviting us to explore the unknown. One such theory is modified Newtonian dynamics, or MOND. Proposed by Israeli physicist Mordechai Milgram in 1983, MOND suggests that the laws of gravity we know might need a tweak when it comes to galaxies. Instead of invoking dark matter, MOND proposes that gravity behaves differently at very low accelerations, like those found in the outer reaches of galaxies. It's like saying that the rules of the game change when you're far from the action. MOND can explain the rotation curves of galaxies without dark matter, but it struggles with some other cosmic observations, like the behavior of galaxy clusters. It's a bit like a detective who can solve some cases, but not others. Another intriguing alternative is the idea that dark matter might not be a new type of particle, but rather a manifestation of something else entirely. Some theories suggest that dark matter could be a result of extra dimensions, as predicted by certain versions of string theory. Imagine our universe as a sheet of paper and dark matter as the shadow of something happening in a higher dimension. This idea is still purely theoretical, but it's a fascinating way to think about the invisible force holding galaxies together. However, it's important to note that these theories are still speculative and lack the robust experimental evidence that supports the dark matter hypothesis. Then there's the idea that perhaps our understanding of gravity is incomplete. Some physicists propose that gravity might not be a fundamental force, but rather an emergent phenomenon, arising from something more fundamental. This is a radical departure from our current understanding, but it's not without precedent. After all, even the concept of atoms was once considered radical. If gravity is indeed emergent, it could explain the behavior of galaxies without the need for dark matter. But this is a complex and challenging idea, and it's far from being accepted by the mainstream scientific community. It's a bit like suggesting that the rules of the game aren't just tweaked, but entirely different. Modified Newtonian dynamics, MOND. In the vast, dark expanse of the universe, galaxies spin and dance in a cosmic ballet that has long baffled astronomers. The outer stars in these galaxies move too fast, defying the gravitational pull predicted by Newton's laws. This conundrum has led scientists to propose the existence of dark matter, an invisible substance that exerts gravitational force but emits no light. Yet, an alternative explanation has emerged, challenging our understanding of gravity itself: modified Newtonian dynamics, or MOND. This theory suggests that the anomalies observed in galactic rotation curves might not be due to unseen matter, but rather a modification of Newton's laws at low accelerations. The tension between MOND and the dark matter hypothesis highlights the complexities of modern astrophysics. Both theories attempt to explain the same observations, but they do so in fundamentally different ways. Dark matter offers a straightforward solution within the framework of general relativity, while MOND challenges our basic assumptions about gravity. This debate is far from settled, and new observations and theoretical developments continue to shape our understanding. As we delve deeper into the mysteries of the universe, the interplay between these competing ideas will undoubtedly lead to a richer, more nuanced picture of the cosmos. Challenges and controversies. Dark matter, the enigmatic substance that makes up approximately 27% of the universe's mass energy content, remains one of the most perplexing mysteries in modern astrophysics. Its presence is inferred through gravitational effects on visible matter, like stars and galaxies, yet it neither emits, absorbs, nor reflects light. This invisibility poses significant challenges to scientists attempting to study and understand it. Imagine trying to map an iceberg while only seeing the tiny tip above water. The vast majority of the iceberg, like dark matter, remains hidden from view. This analogy underscores the difficulty in directly observing and measuring dark matter, making its study a complex and indirect process. One of the primary challenges in studying dark matter is its elusive nature. Unlike ordinary matter, which interacts with electromagnetic forces and can be detected through various means, dark matter interacts only gravitationally. This means that scientists must rely on indirect methods, such as observing the gravitational effects on visible matter, to infer its presence. For instance, the rotation curves of galaxies provide crucial evidence for dark matter. Stars on the outer edges of galaxies move at speeds that suggest there is far more mass present than what we can see. This discrepancy implies the existence of a massive, invisible component, dark matter, holding these galaxies together. However, this indirect approach leaves room for uncertainty and debate. Controversies arise from the various theories proposed to explain dark matter. The leading hypothesis suggests that dark matter consists of weakly interacting massive particles, WIMPs, which have yet to be detected despite extensive searches. Alternative theories propose that dark matter might be composed of axions, sterile neutrinos, or even more exotic particles. Each theory comes with its own set of challenges and uncertainties, fueling ongoing debates within the scientific community. For example, the absence of definitive evidence for WIMPs has led some researchers to question the validity of this hypothesis and explore alternative explanations. This scientific tension drives innovation and collaboration, as researchers strive to unravel the mysteries of dark matter. The search for dark matter is not just a theoretical pursuit. It has practical implications for our understanding of the universe. Dark matter plays a crucial role in the formation and evolution of galaxies, influencing their structure and dynamics. Without dark matter, the galaxies we see today might not exist in their current forms. This underscores the importance of resolving the challenges and controversies surrounding dark matter. As scientists continue to develop more sophisticated detection methods and theoretical models, the hope is that we will one day uncover the true nature of this invisible force, shedding light on one of the universe's most enduring mysteries. The future of dark matter research. Dark matter, the elusive cosmic glue that binds galaxies together, remains one of the most profound mysteries in astrophysics. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. Yet, its gravitational effects are undeniable, like a ghostly puppeteer orchestrating the dance of stars and galaxies. Scientists have mapped its presence through its gravitational pull, much like deducing the existence of a hidden room by the drafts seeping through the walls. The future of dark matter research is poised to delve deeper into this enigma, with several promising avenues on the horizon. One of the most tantalizing prospects is the continued development of advanced detection technologies. Experiments like the Large Hadron Collider, LHC, and the Axion detector are pushing the boundaries of what we can observe. These tools are designed to capture the faintest whispers of dark matter particles interacting with ordinary matter. It's akin to trying to hear a whisper in a hurricane, but each technological advancement brings us closer to deciphering the language of the cosmos. The next generation of detectors, currently in the planning stages, aims to be even more sensitive, potentially unveiling the first direct evidence of dark matter particles. Another exciting frontier is the exploration of dark matter's role in the early universe. By studying the cosmic microwave background radiation, the afterglow of the Big Bang, scientists can glean insights into the distribution and behavior of dark matter in the infant cosmos. This is like reading the rings of a tree to understand its growth and the environment it endured. Upcoming missions, such as the Euclid Space Telescope, will map the large-scale structure of the universe with unprecedented precision, providing a treasure trove of data to unravel the secrets of dark matter's evolution. Moreover, the intersection of dark matter research with other fields, such as quantum physics and cosmology, promises to yield groundbreaking discoveries. Theories like supersymmetry and axions offer intriguing candidates for dark matter particles, bridging the gap between the quantum world and the cosmos. Collaborative efforts between theoretical physicists and experimentalists are crucial in this endeavor. It's a bit like a detective team, each bringing their unique skills to solve a complex case. As our understanding of fundamental particles deepens, so too will our grasp of dark matter's nature and its role in the universe. The journey is far from over, but each step brings us closer to unraveling one of the greatest mysteries of our time. Unraveling the cosmic mystery. In the vast, dark expanse of the universe, galaxies spin and dance in a cosmic ballet, bound together by an invisible force. This force, dark matter, is a cosmic enigma, a mysterious substance that doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is undeniable, its gravitational pull holding galaxies together, influencing their structure and evolution. It's like a cosmic puppeteer, pulling the strings from the shadows, unseen but ever present. Picture a spinning merry-go-round. Now, imagine if the horses on this merry-go-round were moving so fast that they defied the laws of physics as we know them. This is the puzzle that dark matter presents. Galaxies rotate at such high speeds that the visible matter within them, stars, gas, and dust, shouldn't have enough gravitational pull to keep them from flying apart. Yet, they don't. Something else must be at play, providing the extra gravitational glue. This something is dark matter, making up about 27% of the universe's total mass and energy content, far outweighing the visible matter we can see and interact with. The search for dark matter is like a high-stakes game of cosmic detective work. Scientists have proposed various candidates for dark matter, including WIMPs, weakly interacting massive particles, axions, and sterile neutrinos. Each of these particles is theorized to interact weakly with normal matter, making them incredibly difficult to detect. Yet, the hunt continues, with experiments like the Large Hadron Collider and underground detectors like Xenon and LUX searching for these elusive particles. The stakes are high, for understanding dark matter could revolutionize our understanding of the universe, shedding light on its origins, evolution, and ultimate fate. It's a mystery that has captivated scientists and the public alike, a testament to the enduring allure of the unknown. As we pull back from the cosmic dance of galaxies, remember this: dark matter is the unseen puppeteer, the cosmic glue that binds the universe together. It's like the wind. You can't see it, but you see its effects in the rustling leaves and the swaying trees. We've seen its fingerprints in the swirling galaxies, in the bending of light, and in the very structure of the cosmos. We've journeyed from the spirals of galaxies to the edges of our understanding, and yet, the mystery deepens. Dark matter is out there, shaping the universe, and we're just beginning to understand its language. It's a puzzle, a cosmic whodunit, and we're all detectives, piecing together the clues. So what's next? Join us as we continue to explore the invisible universe. In our next adventure, we'll dive into the mind-bending world of black holes, where space and time themselves seem to break down. Will we find answers, or will the mystery deepen? There's only one way to find out. Don't forget to like, share, and subscribe for more cosmic journeys. Together, let's unravel the secrets of the universe, one mystery at a time. The cosmos is calling, and we're just getting started. See you in the next video.